Hey everyone, welcome back to another video. Today we're going to be going through redox and electrochemistry. So these topics were ones that I found very challenging because even though I knew roughly what was going on, I found the way that ACER examines it quite difficult and a lot of traps and just generally quite tricky. So what I'm going to do today is go through the basics of redox and electrochemistry, but also integrate that with a lot of the ACER practice material so you can kind of see the application of the knowledge that we're learning as well. As I said, it's a tricky topic, so I think this will be really useful for everyone sitting the GAMSAT. Okay, so let's dive right in. So redox reactions are just reactions where electrons are being transferred. And I've kind of written here, it's the combination of these two words, portmanteau, if you will, of reduction and oxidation just combined. And basically, the thing that's reduced is gaining electrons, and the thing that's oxidized is losing the electrons. So one thing's losing them, the other one's taking them. It's always a transfer. And that's a really important concept. And how you can remember that is this mnemonic or acronym, which is oil rig, and that just says that oxidation is loss, reduction is gain. So this can be useful, but I do find it has its limitations. So don't put too much weight on this. I'm going to show you another technique to determine if it's oxidation or reduction, but this can be helpful. Okay, so oil rig, and basically what we're doing when we're talking about redox reactions is where something's being transferred, electrons are being transferred from one thing to another. So I mentioned I had a better way to determine if it's oxidation or reduction. And basically what we're going to do is in our molecule, so we're going to draw it out, and then we're going to add all the positive things and all the negative things, and then spread the difference between the carbons. So I'll go through an example of this in a second, but really the only examples I've seen are hydrocarbons. So these have hydrogen, oxygen, and then carbons as well. So all the positive things are going to be the hydrogens, which have a +1. So you just need to remember these, but luckily they are just the charges of those atoms. So hydrogen is +1 and oxygen is -2. Okay, so you're going to draw out your molecule, write down +1s and -2s everywhere, and then add up all the positives, add up all the negatives, and whatever the difference is, you spread that across the carbons, because overall the molecule needs to be 0. One little caveat to that is if the molecule's charged. So if the molecule has a -2 charge, you need to add up all the carbons so that it equals -2. This will make a little bit more sense when we go through an example, but I just wanted to kind of lay the foundations here. And what we're going to be doing to determine if it's a redox reaction or not is see if the charge or the number on any of those carbons, it's called an oxidation number. So we're going to see if the oxidation number changes across the carbons between the reactant and the product. And if it does, it's a redox reaction. If not, then it's something else. And I'll go through two examples in a second. One's redox, one's not. And I'll show you how you can kind of determine what kind of reaction it is if it's not redox. So one last time, add the positives, add the negatives. Okay, so this is question 53 from the sample questions booklet. I've written it up there in kind of a shorthand form. And remember that the hydrogen is +1 and the oxygen is -2. Now, you need to interpret a few things in the text, but hopefully what you can uncover is that we have an alcohol like this thing on the left. I've just drawn methanol, and then it reacts with ADH, which is just an enzyme, and it becomes this methanol. So it becomes an aldehyde. So I've skipped that kind of part of the question because what I wanted to focus on is using that application of oxidation numbers. So as I said, we write in all the positive things. So these hydrogens just become +1. The oxygen is -2. And if we add all of these up, we have 4 positive hydrogens, so that's +4. And then we have 1 -2. So therefore, for this to be equal, the carbon is -2, because that will give us an overall charge of 0. And I know that because the overall molecule has a charge of 0. So this is what I was talking about before, If this molecule, it said, is negatively charged or something, that's going to change the charge on the carbon. But because we don't have that, and we have a neutral molecule, which you usually will in these kinds of questions, we know that the carbon has to be -2 because that will mean that the overall charge is 0 because we've got 4 positives and now we have 4 negatives as well. And then we just do it again with the other molecule. So again, we have +1, +1, and -2. And now we can see that we have 2 positives and 2 negatives. So this carbon is now 0. So we've gone from -2 to 0. So this, if there's a change in the carbons at all, it's instantly a redox reaction. Now what you can see here is we've actually increased by +2. Now the easy way to remember this is that if the number reduces, it's reduction. So our number has not reduced, it's actually increased. So therefore, this is an oxidation. Now I have seen some questions as well that might ask how many electrons have actually been transferred in this reaction. So luckily, this actually tells you how many have been transferred, and the number is 2. And we know that because it's an oxidation, we can do our oil rig. We know that oxidation is loss, so we've lost 2 electrons. And that kind of makes sense because electrons are negatively charged. So if we've gone more positive, it means we've lost some electrons because the oxidation number has increased. So hopefully there's a few different ways that I've given you there that you can determine if it's oxidation or reduction. And from that, if you just kind of take your time and just think it through, because it is tricky because a lot of double negatives. So, there's a loss of negative charge. That stuff gets confusing. So just take your time and work through it. But if you kind of go back to those core principles, you should be able to do okay. So we've found out that the methanol is oxidized to methanol, and that means that this ADH here, this has been reduced. Sorry if you can't see that yellow very well, but it's been reduced because, again, it's a transfer of electrons. So something is oxidized, something's reduced. The methanol is losing its electrons, and the ADH is taking them. It's gaining those electrons. So that's the oil rig. Now, the last little confusing thing, and it's another double negative, is that the thing that is reduced is actually the oxidizing agent. Okay, so oxidizing agent. So the ADH is reduced, but it's the oxidizing agent. Now, it kind of makes sense when you think about it because it's being reduced, it's allowing the other thing to be oxidized. So because it's getting reduced, it's allowing the other thing to be oxidized, therefore it's the oxidizing agent. So just keep in mind that the thing that does the oxidizing is the oxidizing agent. The thing that does the reducing is the reducing agent, but it's not always a straight kind of, it's not always the same thing. It's actually always the opposite. So just keep that in mind because there are questions that ask what's the strongest oxidizing agent or something like that. And you need to realize that's actually the thing that's being reduced. So that's another little way that they can trick you sometimes. Again, I think it's all about just having a really good understanding of these basic principles and then just taking your time, recognizing that it's a situation where there's a lot of double negatives. Take your time and think through it and you should be able to reach an answer. So sorry to interrupt what must be a really enthralling video, but I'd love it if you could like, comment, and subscribe. It really helps me grow the channel and encourages me to make more videos. So if you could take a quick second just to give me a like or subscribe to the channel, it really helps me out and I'd appreciate it a lot. And here's another one. So practice questions booklet, question 38. I've written it up there as well. And it basically, in this one, they actually give you the 2 molecules and they say, what type of reaction is this? Now, because they're quite large, I've gone through and I've already done all the numbering. And you can see that there were 4 positive hydrogens here and then 8 negatives on the oxygens. So that's a difference of 4. And I've just spread that 4 amongst all these carbons. So they all have +1. I might actually highlight them. That'll be a bit better. So they're all +1. And if we look at the next molecule, we've got 6 hydrogens now and a bunch of oxygen. Now I've done all the charges, but you can see that the difference is still 4. And when we look at all the carbons, therefore, because there's still 4 carbons, it's actually still +1 on all of those carbons. So because the number hasn't changed, we instantly know it's not a redox reaction. Now, I think if you just look at the words that they use, you should be able to figure out what kind of reaction it is. So how I like to do these is just kind of scribble out everything that's the same on both sides. So I'll scribble out that COOH, scribble out that one as well, scribble out that CH, scribble out another CH. So that means I'm left with one H and an OH. So that means I'm left with H2O. So the difference between these two is that I've added H2O. So that should be a hydration reaction. If I'd lost H2O, dehydration. If I'd gained just hydrogen, hydrogenation, sorry. So you should be able to figure out if it's not redox, you should be able to just look at what's changed and hopefully figure out what kind of reaction it is. Okay, so next are these reduction potential tables. Now, basically, how I like to think of these is there's a list of numbers here, and that just determines the total energy if one of these things goes in that direction. So what I mean by that is if you go from this left side to the right side, so if you progress this way, it's a bit hard to see the colors, but if you go from left to right, then whatever this number is, that's how much energy you produce. So basically when we're doing, when we're making batteries or things like that, you put together multiple of these half reactions because this is a reduction. Now remember, we need to have a reduction and an oxidation. So we pair two of these reduction and oxidation reactions together, add together the numbers, and that will give us some amount of electricity that's produced in that reaction. That's kind of how I think about it on a basic level. Now, why they give us these tables and why, or what we're going to need to do with these tables is determine what reaction is going to be reduced and what's going to be oxidized. So I've written a few little rules down here which I think are helpful just to set the scene before we get stuck in too much. But only one reaction can run as a reduction. So that should make sense because we're always transferring electrons in redox chemistry. So you can't have two things being reduced because if they're both gaining electrons, where are the electrons coming from? So something has to be giving those electrons. So we pair two together and one of them runs as a reduction, one runs as an oxidation. And if we look at this table, remember I said these are reduction potentials. So if one's running as an oxidation, but we only have the reduction potential, we need to actually flip the sign of that number and that will give us the oxidation potential. So with this table, so for example, with this first one, this would be, so the reduction potential is -2.9. The oxidation potential will actually be +2.9. Okay, so so depending on which way the reaction's going, that's going to be the opposite number. So the same number, but the opposite sign. Now, once we know which one's running as a reduction, and I'll get into exactly how we do this, but I just want to give more of an overview first. When we know one's running as a reduction, so let's say we're running this one as a reduction, and then we're running this barium one as an oxidation, so notice that I haven't used that negative because I'm using the oxidation potential because barium's going to be oxidized. So once I've got the oxidation and the reduction potential, I just take those and add them together. So in this case, the E cell would be the reduction, which is +0.8, I'm just rounding, +2.9. So that would equal 3.7. Sorry about my writing, it's horrible. So that would be the total energy in the cell. Now, very important concept is that this number has to be positive for the actual reaction to proceed. So there are some cases where you add the two numbers together and it's actually negative, that means nothing will happen. Okay, so that's a very important concept. So I've spoken about once we know which one's an oxidation, which one's a reduction, that we can just add those numbers together. But how do we actually figure that out? So there's a few different ways. So if you have two solutions, so I might just focus firstly on these reactions. I'll zoom in a little bit here. So you notice each of these reactions has this equilibrium sign. So that means that the reaction can actually go either direction. So we could go to the left and we could go to the right. And what determines that is the reduction potential or the oxidation potential. So if you had two solutions with all of the ions in there, so you had this and you had all the ions, and you had this with all the ions, the number which is more positive will run as the reduction. Now, this will be exactly the same for the oxidation, okay? So the more positive runs as the preferred reaction. That's how I kind of think of it. So if we look at these ones, we have positive 0.8 for AG, and we have negative 2.9 for BA. So therefore, the AG being more positive will run as the reduction, and that forces the BA to run as an oxidation. And that's when we flip the sign into that 2.9 into the other oxidation number. Now, unfortunately, that's not the end of the story. So that's if you had all of the ions in the solution there, but sometimes they are a little bit tricky and they only give you one of the ions. So they might say, if you added PB solid, so for example, this one here in blue, if you added that to the AG, what would happen? Now that's a little bit tricky because this PB here has actually already been reduced. If we look at the left-hand side, we've got PB2 plus 2 electrons, okay? So that PB2 plus takes on those electrons, so it's gaining the electrons, so therefore it's being reduced. And this here on the right, the PB no charge, has gained those electrons, it's been reduced, it's already in its reduced form. So you can't reduce it anymore. It can only be oxidized. So that's where they can trick you sometimes, is they give you one certain ion, but therefore you can't use that reduction potential because it's not possible to reduce that ion anymore. It has to be run as a oxidation. So that's where you would use the oxidation potential. So they can be very tricky, and this is why I just think take your time when you're going through these and don't fall for any of those traps. All right, so let's do an application of the reduction potentials now. So I'm going through question 29 and 30 from the practice questions booklet. So you get this when you register for the GAMSAT, so everyone should have this one. And we'll just start with question 29. So I've summarized a little bit, but I've basically just redrawn out the reduction potential table and said, and the question's asking, what would happen if Br2 is added to Cl minus and I minus? So this is exactly what I was talking about before, is they're being very tricky and they're only giving us certain ions. So immediately we know that Br2 can only be reduced. It can only go to the right-hand side because it's currently in its oxidized form. So we can't further oxidize that. It can't lose any more electrons. It has to gain these electrons. So we know that this is the thing that's being reduced. Unfortunately, that's not an option. So what we actually need to do is, because we know that's being reduced, we know that the other two are going to run as oxidation reactions. So we actually need the oxidation potential of these two reactions. So this plus 1.36 now goes to negative 1.36 for the chlorine. And the iodine goes from plus 0.54 to negative 0.54. So And yeah, and same thing as the bromine, these two, the chlorine and the iodine, can only be reduced. They can only be oxidized. They can't be reduced because they're already in their reduced form. So chlorine and iodine have to go to the left, and then Br has to go to the right. So that means these kind of potentials are actually out of play in this question because they can't be reduced. So we know that Br is going to be oxidized, and then we're going to take these oxidation potentials. Now remember, the E cell is just adding up these two. So we have +1, basically. I'll just do 1.07. And then we can just take both of these. So if we take the chlorine, it's actually negative 1.36. So this will in total be a negative number. And remember I said if it's a negative number, nothing will happen. So in this case, nothing actually happens. So nothing happens with the chlorine. However, if we do the same thing with the iodine, we can see that it's plus 1.07 minus 0.54, and that will be roughly positive 0.05. So this reaction will happen, and the iodine will be oxidized because that's got an oxidation potential that is suitably low, such that the reduction potential will be positive when you add them together. So I hope that makes sense. It's a little bit tricky, but you need to figure out which one's running as a reduction, find that number, find out which one's running as an oxidation, find that number, and then add them together. And just remember that it has to be positive for the reaction to happen at all. And moving on to question 30, very similar question in the end. It's saying which one would reduce H+. So for H+ to be reduced, remember the more positive reduction potential will run as a reduction. So this number, which is 0, has to be more positive than whatever else it's with. So if we look at these, we've got I2, we've got Cu, and we've got Zn. So if we think about this, we've actually got I2. Now, because where it is, it actually can only be reduced, if you think about it. It's already in its oxidized form. It's already lost electrons. So the only thing it can do is actually gain electrons. Now, if it's gaining electrons, that means that the hydrogen would have to be oxidized. And the question's asking which one would reduce hydrogen. So we need the other one to run as an oxidation. So that means it can't be iodine, because iodine can't run as an oxidation in that form. We would need the I minus rather than the oxidized form. So moving on, so now we have copper and zinc. Now again, because these are running as oxidations, we need to take their oxidation potential. So this would go from plus 0.34 to minus 0.34. And this minus 0.76 would now become positive 0.76. Excuse my writing again. And now it's very much the same case as before. So whichever one is more positive, whichever oxidation potential is more positive, is going to run as an oxidation. But we also need to add them together separately. So if we add together the hydrogen's reduction potential, which is 0, with the negative number, that's going to give us a negative number. So nothing's going to happen with the copper. It just won't react. It won't be a redox reaction. But if we compare that to the zinc, we can see that it's 0 plus 0.76. So this would give us a positive E cell, and therefore the reaction would proceed. So the only thing which would actually reduce the H plus is zinc, and that's answer C. So I hope that kind of gives you an idea of how you're going to need to go through these questions if you get one. You're going to need to find what needs to be reduced or what is going to be reduced, and then what's going to be oxidized, and maybe calculate the oxidation potentials depending on which way the reaction's going. So it's very, very important to find what ions they're giving you, because that will actually dictate which reactions are possible and which ones aren't. So very important step to do that. and then calculate potentials and add them together and make sure that the E cell is positive. Now, there were a few more questions in that stem, but I didn't want to kind of get too off track. I feel like that's all the basic stuff that you need to know for redox and electrochemistry. So I'd like to leave it there, but I hope you found that useful. If you have any questions, feel free to ask them in the comments. And yeah, if it was useful, if you did find the video useful, I'd love it if you could like, comment, and subscribe, and I'll see you in the next video.